So now we're going to talk about the ionic solids. Many ionic solids have crystalline structures that are similar to those unit cells that we've looked at. But the complicating factor here is that you have to have two different kinds of particles. You have cations and anions. And so you've got variations in size. You could have two ions that are similar in size, or one might be much larger, and that's going to affect the crystal structure. You also have issues of charge neutrality. If you have like a positive 3 ion and a negative 1 ion, you need 3 times as many of the negative 1 ions, and that's going to affect the crystal structure. So we're just going to look at some different examples to give you just an idea of what this is all about. Like this says, in general, the more similar the size of the cation and the anion, the higher the coordination number. So if they are more similar in size, they're going to be able to pack in closer together. So ionic solids with ions that are similar in size. An example is cesium chloride. For cesium chloride, the chloride ions are going to occupy the lattice points of a simple cubic unit cell, and the cesium atom is going to sit in the center of the cell. So this unit cell then would contain one of each ion. What we looked at before would be just the green ones and ignore the purple one, and we said that would have one atom in it, right? Because you have an eighth of this one, an eighth of that one, etc. So you have one chloride ion in here and the cesium atom in the middle. So the coordination number here is going to be 8 because we're not looking at chloride ions connecting with each other. We're looking at cesium connecting with chloride ions. The cesium here in the center is in close proximity to all 8 of those ions, so that's the coordination number. Calcium sulfide is another ionic solid where the ions are similar in size and they'll form this structure. If ion size was the only consideration, things would be very different. So in sodium chloride, the sodium ions are much smaller than the chloride ions. If you think of these as maybe being apples or oranges are rounder, oranges and cherries, and you put them in a box, right? You could get a lot of cherries to fit around the oranges because they're so much smaller. But you can't do that with an ionic compound because you have to have equal numbers of sodium ions and chloride ions. So each sodium ion has to be surrounded by an equal number of chloride ions. So the way salt typically forms is it will form in the face-centered cubic structure. So here's one chloride ion at the face and chloride ions at the corners. And then the sodium ions will be in between those. This is known as a rock salt structure. And remembering face-centered cubic, bless you, a face-centered cubic unit cell is going to have 4 atoms in it. So you have half of the one at the face, and there's 6 of those, so that's 3 atoms or ions, and then you have an eighth of each at the corners, so a total of 4. If it has 4 chlorides, there's going to be 4 sodium ions as well. Yes? Are the cations always in the center? Well, it's really a matter of which one are you focusing on, because you could also focus on the sodium ions and see that there's a lattice, the same lattice with them, and then the chloride ions would be in the middle. So sort of depends on what you're focusing on. Okay. But they will always be, negative anions will always be surrounded by cations. Cations will always be surrounded by anions. Because what's holding this together is the force of attraction between the oppositely charged particles. So these guys are attracting each other. This chloride ion and that chloride ion are kind of repelling each other. They don't want to be too close, but there's the attraction, and this chloride are attracted to the sodium that's in between them. If you have large size differences, you're going to end up with a lower coordination number. So the example here is zinc sulfide, which is a mineral known as zinc blende. And what happens here is the sulfide ions are taking on a face-centered cubic. There's one of the faces, and there's the one in the center. Face-centered cubic. And the zinc ions are going to occupy what are called the tetrahedral holes in this structure. So here we have a tetrahedral hole. We have 4 sulfide ions, and they are in the shape of a tetrahedron. The zinc ion fits into the hole in between them. So this is different than having the zinc ions over here. Now the zinc ions are going to be in these little holes. These sticks here are not representing bonds, but they do represent the 4 interactions that zinc ion has. So now the coordination number is 4. This unit cell also contains 4 of each atom, but there's more empty space in it. Any questions? Mm-hmm.
So that means the more empty space is the less efficient space that we use, or is it the opposite of that?
The more empty space, the lower the packing efficiency.
Okay.
So packing efficiency, you think about packing fruit. You want to be efficient, get as much in as possible, right? You don't want a whole bunch of empty space. So high packing efficiency means there's a lot of atom or substance and very little empty space. That's going to affect the density of the substance. So this zinc blende would have a lower density than if it could form a different crystalline structure where things would be closer together. If you have ions with different charges, things, just get more interesting. There's calcium fluoride. So we have 2 fluoride ions for every calcium ion. This is going to adopt what's known as the fluorite structure. Fluorite is calcium fluoride, so this structure is named for that mineral. Here we have calcium ions at the face of a face-centered cubic unit cell, and there are 8 tetrahedral holes in there, and so a fluoride ion can be in each of those 8 holes because you need 8 fluoride ions for the 4 calcium ions. So if we count up how many ions are in here, these 8 fluoride ions are completely within the unit cell, so there's 8 of those, and there's 8 of the calcium, there's 4 of the calcium ions. Yeah, face-centered. So that's the fluorite structure. If you have a +1 cation and a -2 anion, you have exactly the opposite situation, and so that's called the anti-fluorite structure. Don't freak out about trying to memorize all these structures and things. The questions on exams will be more general knowledge. But depending on what you're going to go on to study, you need to at least have heard about this stuff so that you're not completely in the dark when you start learning about it. Okay, so I wouldn't ask this as an exams question, but it's a good question in lecture. Which compound is most likely to crystallize in the zinc blende structure? Well, let's go back to that slide. Oops, there it is. Zinc blende, and ask ourselves, okay, what are the requirements for this structure? Well, what about the ratio of cations and anions? What is it here? 1-to-1, right? So you have to have 1-to-1 cation to anion, so that means they must have equal charges. The other thing here is we have a large size difference. So one of them is very small and the other is quite large. The large one occupies the face-centered cubic unit cell, and the little one fits in the little holes in between. So that's what we're looking for to answer this question. So one of these we can eliminate right away based on charges. Which one? B. In B we have MgCl2, a plus 2 and a minus 1. That's a 1-to-2 ratio, so that can't work. That could be fluoride or anti-fluoride, but it can't be zinc blend. Now looking at these other two, the other thing we said was it was going to have a large difference in size. So the radii are given here, 148 and 181, 96 and 216. So which one has a bigger difference? C. So that would be the correct choice.